Welcome back to the deep dive. Today we're heading off-world to Mars. But forget sunny red landscapes for a moment. We are diving straight into, well, total winter darkness and unbelievable cold. And here's the strange part. In these utterly extreme frozen conditions, scientists have just found this massive, unexpected surge in a really crucial atmospheric gas. So our mission for this deep dive is to unpack these brand new observations about Mars's north polar vortex. We're focusing right in on this recent discovery. They're calling it an unusual surge in ozone. And we want to figure out what this, localized buildup of gas tells us about the chemical history, maybe even the ancient history of the red planet.
Exactly. And what's really cool is that the source material for this discussion comes from very fresh research. It was just presented by Dr. Kevin Olson at the EPSC-DPS joint meeting. So we're synthesizing those key findings, trying to understand first why this surge happens, the physics and chemistry behind it, and second, connecting that atmospheric quirk to the much bigger question: could Mars have ever actually supported life long ago?
Okay, let's start with the basics then. This polar vortex thing. We hear about it causing wild weather swings on Earth, but on Mars, it's fundamentally tied to the planet's tilt, isn't it?
That's right. Mars is tilted on its axis by about 25.2 degrees, which is surprisingly similar to Earth's 23.5 degrees, and that tilt means Mars gets distinct seasons. So when the northern hemisphere tilts away from the sun, at the end of summer you get this plunge into darkness at the pole, temperatures plummet, and this huge swirling vortex of cold air forms over the North Pole, and it just sits there spinning away right through the Martian spring.
And you said the conditions inside this vortex are different, not just a bit colder, but profoundly different.
Oh, vastly different. It's way more extreme inside than outside the vortex boundaries. Think of it like an atmospheric container. It stretches from near the ground up to maybe 30 kilometers, and the air trapped inside. It's characterized by this intense cold. We're talking something like 40 degrees Celsius colder than the air just outside the vortex edge.
40 degrees Celsius colder?
Yeah.
That's a serious temperature drop. It really is like an isolation chamber in the atmosphere.
Yeah.
Does this vortex ever, wobble or change shape? Because if it just stays locked over the dark pole, how on earth do scientists even study what's going on inside?
That's the challenge, but it's also the key opportunity. Just like our own polar vortex here on Earth, the Martian one isn't always perfectly stable. Sometimes it can kind of lose its nice circular shape, become unstable, and actually drift southwards towards the middle latitudes. And for the scientists, that moment of instability is pure gold. It's this rare chance to actually get a look inside that extreme environment, often from a viewpoint where there's still some sunlight.
Right, so this instability gives them a peek inside, and what they're finding is this core chemical puzzle. Inside this super cold, pitch black winter zone, ozone levels just shoot up dramatically. Why? Why does turning off the sun and making it incredibly cold suddenly cause this gas concentration to spike?
It's a fascinating mechanism. It basically boils down to getting rid of the main thing that usually destroys ozone on Mars. The whole process depends on that extreme cold, combined with the fact that Mars only has a tiny amount of water vapor in its atmosphere to begin with. Because it gets so incredibly cold inside that vortex, what little water vapor is there just freezes out. It condenses and basically settles onto the carbon dioxide ice cap below. So effectively, the water vapor just disappears from the air inside the vortex.
Okay, removing the water vapor is key. But why is the water vapor the problem for ozone in the first place? Why does it act like an ozone killer on Mars?
Yeah, this is where the atmospheric chemistry gets interesting. Under normal Martian conditions, with sunlight, ozone gets broken down. Ultraviolet light from the sun hits that small amount of water vapor, H2O, and it breaks the water molecules apart. This creates highly reactive molecules, things called hydroxyl radicals, OH radicals, and these hydroxyl radicals are, well, they're incredibly aggressive chemically. They're the main culprits of things that rapidly destroy ozone molecules in the atmosphere. So logic follows. When you remove the water vapor, the source material for these ozone-killing radicals, by freezing it out, that whole destructive chemical pathway just shuts down. It can't happen anymore. And since there's nothing actively destroying the ozone, it simply starts to accumulate. It builds up inside the polar vortex. It's like the cold preserves it by removing its enemy.
That makes perfect sense. The cold acts like a physical filter, removing the source of the chemical killer. And as Dr. Olson pointed out, ozone is really important because it's this very reactive form of oxygen. Studying it tells us about how fast chemistry is actually happening in Mars's atmosphere. Okay, So we understand this chemistry happening right now. Let's make the big leap. What does this deep winter chemistry today tell us about the chemistry that might have occurred billions of years ago, back when Mars was maybe warmer, wetter? Why does this ozone surge matter for, the grand story of the red planet and the search for ancient life?
Right. Connecting it to the deep past is crucial. Understanding how ozone behaves now under these extreme conditions helps scientists refine their models of how Mars's atmosphere evolved over geological time. And critically, it helps address the question, did early Mars ever have a substantial protective ozone layer? Maybe something a bit like Earth's. Because if Mars once had a significant ozone layer, that completely changes the picture of its early habitability. I mean, think about what ozone does for us here. It shields the Earth's surface from the most harmful, DNA-damaging ultraviolet radiation from the sun. Without that shield, any life trying to get started on the Martian surface would have been, well, constantly fried.
So if that shield existed, even for a while in Mars's past, the odds that ancient life could have survived near the surface go way up. That's the astrobiology game changer, right?
Absolutely. A temporary or even patchy ozone layer would have created a much more benign surface environment. It could have allowed liquid water to stick around longer without being instantly broken apart by harsh UV, and it would have offered some protection for the complex organic molecules needed for life. So yeah, this ozone research connects directly to the goals of missions like ESA's ExoMars rover, Rosalind Franklin. That rover's whole purpose, launching hopefully in 2028, is to drill down below the irradiated surface and look for preserved signs of that very past life.
Okay, let's pivot to the how. How do you actually do this science? How do you study something happening in total darkness for months on end? The observation techniques must be really limited.
That's the core technical problem, absolutely. The standard method atmospheric scientists often use is called limb viewing or limb sounding. You basically look at the edge, the limb of the planet, and see how sunlight filters through the atmosphere. The way the light is absorbed tells you what gases are there. But that technique completely fails if there's no sun, which is the case over the pole during the long Martian winter night, nearly 6 Earth months of darkness.
So that instability you mentioned earlier, the vortex drifting southwards, that wasn't just interesting, it was essential for observation.
Precisely. They literally had to wait for the atmosphere to cooperate, to shift those extreme conditions into a region where their instruments could actually get a look. But even then, just seeing ozone wasn't quite enough. They needed to be sure they were really inside the unique environment of the vortex. So they used this really clever collaborative approach involving 2 different spacecraft, 2 different instruments. First, they used the Atmospheric Chemistry Suite, ACS, which is on the European Space Agency's ExoMars Trace gas orbiter. ACS is a spectrometer. It measures the specific fingerprints of light absorbed by different gases, letting them identify molecules like ozone and measure exactly how much is there.
Okay, so ACS measures the what and how much, but how did they confirm the where? How did they know they were definitely inside that super cold vortex air and not just, some other cold patch?
That's where NASA comes in. For that crucial confirmation, they relied on data from NASA's Mars Reconnaissance Orbiter, specifically an instrument called the Mars Climate Sounder, or MCS. MCS works differently. It's a radiometer, basically a super-sensitive thermometer for the atmosphere. It measures temperature profiles at different altitudes. So by combining the data, the researchers could look for the smoking gun, using ACS to see the ozone surge and using MCS at the same time and place to see that sudden dramatic drop in temperature. That temperature drop was the unmistakable sign that they were indeed sampling air from right inside the core of the frigid polar vortex. It's a beautiful example of international science teams working together.
Okay, this seems pretty clear-cut. Cold freezes out water, water removal stops ozone destruction, ozone builds up. Makes sense. But apparently, this result has stirred up some deeper questions in the scientific community. There's a perspective that challenges whether just removing the water vapor is the whole story. What's the issue here?
Yes, this is where it gets particularly thought-provoking. It touches on the basic stability of the ozone molecule itself. The point raised is that even here on Earth, ozone in the stratosphere isn't perfectly stable. It's what chemists call metastable. This means it naturally decays over time. It has a limited half-life. So our ozone layer needs constant replenishment. And that replenishment happens via this huge, slow atmospheric circulation pattern called the Brewer-Dobson circulation.
Brewer-Dobson circulation. Can you break that down a bit for us?
Sure. Think of it like a very slow, planet-wide conveyor belt in the stratosphere. Air rises in the tropics, carrying ozone produced there, moves slowly towards the poles, and then sinks. This process constantly transports ozone-rich air from the tropics to higher latitudes, effectively topping up the ozone layer all the time.
Yeah.
And here's a little irony. Our own polar vortex on Earth actually acts as a barrier, partially preventing this Brewer-Dobson flow from reaching the very coldest, darkest parts of the polar winter.
Okay, so Earth's ozone needs this constant refueling from the tropics via that conveyor belt. Applying that thinking to Mars, well, the Martian polar night is way longer than Earth's, almost twice as long, nearly a full Earth year of darkness in the deepest winter. So even if you stop the active destruction by removing water, shouldn't the ozone just naturally decay away over that incredibly long night? If the refueling isn't happening, why doesn't the ozone level just drop?
That's precisely the puzzle. Even if the hydroxyl radical destruction pathway is completely shut down by the extreme cold, the inherent instability of ozone suggests there should still be significant loss over 6+ months of darkness. Ozone molecules should just naturally break down back into regular O2 oxygen. The fact that they observe such a large buildup instead of decay is perplexing. It leads to the conclusion, which the researchers themselves acknowledge, that maybe, just maybe, something is being missed here. The sheer amount of ozone accumulating suggests there might be some other currently unknown factor at play in the Martian polar night. Perhaps some unknown chemical process that helps stabilize ozone in the cold dark. Or maybe even some slow, low-energy mechanism that's actually producing a little bit of ozone even without sunlight.
Right, we understand this stopping the destruction part now, thanks to the water freezing out. But the why it stays around for so long and even increases part, that seems to be the new mystery. It really highlights that even with fantastic new data like this, the Martian atmosphere, especially its chemistry, still holds plenty of secrets. Lots more to discover. So, wrapping up this deep dive, the key takeaway seems pretty clear. On Mars, extreme cold does more than just freeze things. It fundamentally rewires the atmospheric chemistry. It shuts down the main pathway that destroys ozone, leading to this really unexpected surge inside the polar vortex. And understanding that process, that chemical preservation, has huge implications for how we think about the possibility of ancient Martian life.
Exactly. And it leaves us, and hopefully you listening, with this really fascinating question to ponder. Given that incredibly long Martian polar night, ozone should decay significantly, even without water vapor attacking it. So what unknown factor on Mars might be compensating? What's allowing the ozone not just to persist, but to actively build up over months of total darkness? Is it an unknown stabilizer, a hidden production mechanism? Answering that is surely the next frontier in unraveling the complex and surprising chemistry of Mars's atmosphere.